Okay, cool. Video for Core 2 integration. Okay, so quick overview of integration. Basics, you raise the power by 1, can't spell today, and then you divide by new power. Look for your notes if you want some more detail on this, but it's just a quick revision video. Integrating finds the area under a curve. That's the whole point of integration in Core 2. But even more specifically, if we put in some limits, definite integration, which we are going to do in Core 2, integration finds the area under the curve, which will be between the curve and the x-axis and your limit. So quick diagram to illustrate that. Random function f of x. If we want the area from A to B, if we want this area, we get that by integrating f of x from A to B dx, and that will tell us that red shaded area there. That's the gist of integration. Okay, where I think students are weakest of integration is actually not the actual integration itself, it's to do with indices. So before we even get started in integration, I want you guys to do about 11 indices questions. Some of them pretty easy, some of them are a bit more difficult. Work the way through, and I'll just put up the answer at the end just to flash them up. But make sure you can do all of these because they could ask you anything like this. Okay, so there's 8 problems for you guys to solve. I want you to rewrite these as x to the n. So, for example, the first one, you could rewrite that as x to the minus 1. Easiest one done for you. Give that a go. I'll leave the thing running for a couple of seconds. If you guys could hit pause, work through those, and I'll go through the answers very quickly in a second. So there's the answer to the first 4. Just something I want to point out. People often get this one and this one mistaken. The 3 stays exactly where it is, it's just a coefficient, so it's still a 3 there. And that third there is still a third there. Don't bring the 3 up as well, you're not allowed to do that. So 3 there, coefficient 3, 1/3, coefficient stays as a third. So if you check those through, I'll just put up the answers for the next lot. So the next 2 should be pretty much the same thing. 7 and 8, a little bit more difficult, so I'll go through a couple steps on these ones. So I've taken apart my square root sign using third rules to pull it apart. Now I'm going to do root 2 times root 2, which is going to be 2, and root x over x cubed will give me x to the minus 5 over 2. There we go. Okay, next one, again, pretty tricky. Just treat it like a fraction, multiply the numerator and the denominator. And you get 9 over 4, x to the minus 7 over 2. Just check you can work through all those guys. They could ask you something that difficult. I think that gives you a nice taste of all the different things you could be asked to do in integration. Let's try some difficult integrals then. Okay, start off with a standard indefinite integral, but with a tough equation to integrate. Okay, so root y equals cube root of x plus 3, and we want to find y dx. So the first thing to do is actually find y. This is to address another misconception. Some of you would square the y, and you try and just square it, so you'd get x to the 2 over 3 plus 9. That's not the case. We have to expand the brackets and square things properly. So this is what we get. So the whole thing has to be squared. Now I can expand these brackets like you guys would have at GCSE, but a little bit more difficult. And now we've got an expression which we can integrate. So integral of x to the 2 over 3 plus 6x to the power of third plus 9 dx. So we're going to do that thing, raising the power by 1, divide by new power is the basic rule you want to remember for integration. So we get 3/5 x to the 5 over 3 plus 18 over 4, which you might have put as 9 over 2, x to the 4 over 3 plus 9x. What I've gotten, we have to add c when we're doing indefinite integration. What that means is if you don't have a number there and a number there, you have to put c because you don't know what the original function was that you differentiated. And again, you can just simplify that to 9 over 2. There we go, so that's your final answer. We'll try the same thing now, but we will integrate with some limits. So, if I just add the limits in, do that in red, say we wanted to integrate it between 1 and 8, process is exactly the same. What I've seen some of you do in past papers is try and just put the limits in straight away without integrating. So that would be at this stage, just putting 1 and 8 in, that doesn't actually mean anything mathematically. You have to do the integration first. So we integrate, we're then going to put some square brackets around our solution, put our limits in again, 1 and 8, and then we're going to subtract our limits, and I'll show you guys how to do that. So the limit you put in first is the one at the top of your integrand, which is going to be 8, and we're going to subtract that from 1. So if you guys watch what I do here. So there I've just put 8 in as x for my first certain integral, and we're going to take that away, put some curly brackets around it, and take away with 1 in as x. So that is what your full solution should look like. Then we just need to simplify all of the terms on the right. 1 to the power anything is just going to be 1, so we're just going to get 3/5 plus 9/2 plus 9. And on the right hand side, getting your calculator to evaluate, and you should find that we get 72 plus 96 over 5 plus another 72. Take away the right hand side, and you'll find that you get 149.1 as your final answer. So that is the area under this function between the limits 1 and 8, which links back to what we did at the beginning. So we found the area under that integral between our two limits. Okay, really common exam question that people find difficult is finding the area under a curve bound by a line in a function or by two functions. So I'm going to show you guys how to go through that. Okay, so we have a straight line, which we're going to call line L, and we have a curve which we're going to call curve C, because we're imaginative of our names. So there we go, that's curve C. And we're told 2 points. We've got point B there, which is the minimum of that one, and we've got point A there, which is our intersect, I should say. And the question wants us to find the green region R bound by those two. There we go, so let's call that R. And in this question we're also given the equation of the curve and the line, so let's put those up as well. Okay, notice two things about these quickly though, guys. Y equals q minus 2x, so we don't know what q is, it's an unknown we need to find. We've got y equals x cubed plus minus 9x squared plus pxs. We've got two unknowns, we need to find q and p. Right, we're also told the x coordinates of those 2 points we had earlier, A and B, so let's put those in. So the x coordinate of point A is 1, and the x coordinate of point B is 4. That's all the information we're given. So we've got two equations of the lines, unknowns in there, sketch there, and our minimum points of our, or the coordinates of our points. So first part of the question, part A, is to show that P equals 24, and then find Q. Okay, so for those of you who want to rush ahead, pause the video now and try and use what we've got to find P and Q, but I will go through that now with everyone else. Okay, so what do we know about these lines? We've got to find where point P is. The line with the unknown P in it is the curve equation. What do we know about the curve? Well, we know that it's got a minimum point at B. So if you think back to Core 1 coordinate geometry, we can find that minimum point by differentiating our curve and then setting equal to 0. So we can find when the gradient is 0, which is when we're going to have that minimum point. And we know that the minimum point has an x coordinate of 4. So we can use those two things together to solve for what P is. So let's go through that then. So what they've kind of said there, minimum point is at x equals 4. So they've told us the gradient, dy dx, is 0 when x is 4. And we're going to use those two bits of info to solve this one. So there's our differential. We're going to set that equal to 0, plug in x equals 4, and then solve that for P. So there we go. And if we evaluate that, we can find that 48 minus 72 plus P equals 0. Bit of rearranging, and we can show that P equals 24, right, which is what we wanted. Excellent. Okay, we also need to find Q though, so let's go back up and see what else we know about this. So we know what P is now, let's put that in. P was 24. We need to find Q though. Okay, so if you look at our curves, we know that they intersect at point A. So at point A, the y coordinate and the x coordinates for our curve and our line are the same. So we can use that to solve our equation simultaneously, substitute in x equals 1, and find point Q. So we're going to solve our intersect simultaneously. So we're going to let those y coordinates equal each other, and we're going to plug in x equals 1, because that's the point where they meet. So that one, we're going to go in as x, and then we're going to solve those two simultaneously. So the equation of the line, we're going to set equal to the equation of the curve. There we go. And we know they intersect when x equals 1, so let's put that in as well. And we can just rearrange that, and we should find that q equals 18. Excellent. Alright, so now we can work on to the actual integration part of this question. So I'll just fill q in at the top there. Okay, so the last bit of the question is to find area R, which is the area enclosed by these two. And there's two methods you can use to do this. One method is easier and quicker, and it's the one that edXL will give you marks for. There is another method you can use, the backup, which is a bit more long-winded, but it will get you the same answer. So let's go through these. So we're looking for the area bound by that curve and by that line. The way to do any of these questions is to try and break it down into two shapes. So if we imagine splitting this up into a triangle and a weird curvy bit. So let's take that triangle, that's one of our integrals, and then let's take that weird curvy bit, that's going to be our other integral. Okay, so split it up and neatened it up a bit. Our first integral here is the curve from 0 to 1. Second bit, we've got this triangle. Now we can either integrate the triangle from 1 to whatever that point is, or we can just solve for the area of the triangle. Either way though, we're going to need to find that point. So let's make that be our first point then. Find out when that intersects. So if we go back up to our equation of the line, which is what we're looking at here, when does our line intercept the x-axis? Well, we'll just set y equal to 0. So setting y value of our line to 0 to find out that intercept there. So 0 equals 18 plus minus 2x, add 2x onto each side, and we can find that x is going to equal 9. So we know that point there is going to be 0.9. So let's start off with finding the area of this triangle. So the easiest way will just be to do half of base times height. To find the height of this though, we're going to need to work out what the x-coordinate of our intercept was. So the x-coordinate was 1, we can substitute that into either of our equations to find out what the height of this triangle is. So let's stick with our line equation, put 1 in, and we'll get 18 minus 2, x is 1, that's going to give us 16. So we know the height of this triangle is 16. We have a triangle given by half base times height. We know the base of this is going to be 8, so it's going to be half 8 times 16, which will give us an area of 64 units. Okay, just to show you guys the other method for this, if you did want to use it, we can also just do the integral of the straight line from 1 to 9. It's a bit more long-winded, much more hard work than just the area of the triangle, but we could do that if we forgot, and it's good practice of integration, so we'll do that very quickly now. So we go set up our integral, let's do the integration, there we go, put the limits in, and you find that that also equals 64 units. So either way, area of the triangle is probably a bit easier, but the integration method does still work. Okay, so we've just got to add that area to the area of that weird curvy bit. Now the way we're going to do that is going to be to integrate the curve between 0 and 1. Okay, so we'll set up our integral. There we go. Now we can just do the integration. So we'll get x to the power 4 over 4 minus 3x cubed plus 12x squared. So now we've just got to put our limits in. So limits are going to be from 0 to 1. We can see quite clearly now that putting 0 in is just going to cancel out the whole equation. So we just need to put 1 in. So we get 1/4 minus 3 plus 12, which will give us an area of 9.25. So the total area under the curve is just going to be 64 plus 9.25, giving us 73.25 as our area under that original curve. So just as a brief overview of this, idea is for doing integration to find an area, split it up into two shapes. One of them will normally be a triangle or a square or a rectangle, something you can find the area for really easily, and then with the other shape just do the integration and find the limits. But it is pretty straightforward once you've worked out which shapes you need to use. Okay, that's it for today then guys. Good luck with the revision on integration. Any questions, just drop me an email.